Hello everyone, my name is Sanjeev and I'm here to present NDNViber, which is a vibration-assisted automated bootstrapping technique for IoT devices. This is a project that I have been working on with my colleague and advisor at the School of Computing and Information Sciences in Florida International University. We all know that the IoT paradigm has become a reality, with many devices joining the network and being ably supported in terms of communication by the internet. However, the number of connected devices that were predicted to be present in 2020 has not been reached as yet. A major reason for this is because of the security concerns of such small IoT devices. In this paper, we thus discuss the onboarding of these IoT devices into a network. This onboarding process is also called as bootstrapping and has three main goals. The first being to prevent the device from joining the wrong network, and also to prevent a malicious device from joining the network, and finally to prevent the network from being attacked by some common attacks that happen during the onboarding process, which include impersonation, replay attacks, and man in the middle attack. The process of bootstrapping is, however, very difficult and cumbersome when we have small, highly resource constrained devices with minimal interfaces. To better understand the situation that we are talking about and the scenario we consider, let us consider a leak detector or a flow control sensor that is placed right next to the pipes. Usually, these pipes are enclosed within walls, and hence these sensors are behind the walls and cannot be reached once they are installed. In such a scenario, when we're talking about bootstrapping, which includes the exchange of security keys and other crypto material, we need a way to communicate such messages. It has been seen that traditionally there are auxiliary channels, which are also called out of band channels, that are being used for this purpose. So, as our first goal, we tried to survey all the out of band channels and tried to categorize them and identify their shortcomings and advantages in terms of being usable, being secure, and being scalable in terms of using multiple devices or different types of IoT devices at the same time in a network. With all these aspects that we chose to work with, we see that vibration channels perform well for our scenario, and it becomes more enhanced when we use a request response based data centric communication model that's offered by NDN. Thus, we present NDNViber, which can be used to establish mutual trust even in a highly chaotic, human imperceptible communication environment with minimum or no human interaction. As discussed earlier, NDN ticks most of the boxes that are required in our scenario in being dynamic, highly automated, secure, and robust. The only requirement, though, is that the IoT devices have an associated accelerometer. However, it is seen that modern devices either come with an inbuilt accelerometer, or it's also seen that it's very simple to embed an accelerometer and it's highly inexpensive. Let us now talk about the working of NDNViber. The bootstrapping process followed by NDNViber is split into 4 stages, starting with the pilot sequence followed by the trigger sequence, which is again followed by the anchor exchanges and the NDN search sequence, which ends the bootstrapping. Each of these stages includes NDN-like message exchanges in a hybrid fashion. By hybrid here, I mean it could use either just the vibrations, a mix of vibration and the traditional communication methods, or just the traditional communication methods that the device is built to use. The pilot sequence is the first stage, as seen in the previous slide, and acts as a way to wake the devices up. It's usually seen that these highly resource constrained devices, in order to save on power, try to go into hibernate mode or slumber or idle state, and hence have to be woken up to be active and listening to the vibration channel for any kinds of vibrations. So the pilot sequence is a controlled encoded vibration of sent by the controller or which includes a vibration for about 250 milliseconds and an idle state of about 25 milliseconds. The pilot sequence is followed by the trigger sequence, which includes an NDN interest from the controller to the device, which is present within the vibration range. The vibrations thus sent carries information for the devices about the operating namespace or the environment in which the device would be operating, and auxiliary information which includes cryptographic material, keys, and other details, temporary keys that would be used in further sequences and communication, along with the most important information, which is the channel details that the device would have to use for further communication. The target, which is the IoT device, on receiving these vibrations and decoding them, would be able to identify the allocated channel that it should use for communication and uses this in order to communicate its information about its capability and its name to the controller with appropriate nuances and timestamps to ensure the freshness and authenticity of the messages. The anchor exchange follows the trigger sequence. By now, the device has information of the channel it should use, and hence it triggers the anchor exchange by sending out an interest for the trust anchor's information uh, to the controller. All exchanges and all communication in this phase, that's the anchor exchange phase, happens in the traditional communication medium or mode, which includes either Wi-Fi or Bluetooth, Zigbee, or anything that the device is capable of communicating in. The controller, on receiving the interest, replies with the anchor details, which the device can use for further communication in the network. Finally, we have the NDN search sequence, which is again initiated by the IoT device. At the end of this stage, the device has its own NDN certificate and the private keys. The vibration pattern for each device is different and serves as an important feature in the challenge response phase. Now that we know the working of NDNViber, let us see the encoding scheme that we used in our design. So each octet of the packets via encoding is grouped and independently converted into a vibration duration, which is based on the lookup table that you see on your screen at the bottom left. We see that the vibration motors in Android phones, which we use uh, as the controller in our experiments and our design, is built by multiple vendors, and hence the vibrations less than 50 milliseconds are not considered precise. We also prefer to use an idle period of about 20 milliseconds. This idle period can be tuned based on the sensitivity of the accelerometer that's used in the network and which is associated with the device. This provides two features. The idle period basically determines the end of a vibration and also provides the device with enough time for decoding what it has received. On the bottom right, you can see a typical vibration, encoded vibrations, which includes a vibration duration followed by an idle period, which in our case is 20 milliseconds. Now that we have seen the encoding scheme, let us look at the advantages of using a vibration, and especially vibration duration instead of amplitude, which is what people usually design. We use the commodity Android phone as the controller, and it's seen that all versions of Android provide support for programming the vibration duration, while the same is not true for programming of amplitude of vibration. Also, the use of vibration duration significantly decreases the transmission error. The only factor to be tuned in all cases would be the idle period, which, as I told and have mentioned earlier, depends on the accelerometer that's the sensitivity of the accelerometer that's associated with the IoT device. The computational load on the devices is reduced immensely with the decoding of vibrations using just a simple round off operation. Also, time synchronization becomes less critical because once the pilot sequence is appropriately identified. NDNViber being vibration based is requires a very close proximity. This close proximity actually enhances the security properties of NDNViber because of the requirement of the device and the controller to be within a separation of 1.5 centimeters. The attack surface, including eavesdroppers and other kinds of malicious nodes, decreases drastically. You can see on the screen the uh, intensity of vibration, the way in which it decreases exponentially, almost exponentially, as the distance increases, and at approximately 1.5 centimeters, it goes to zero, meaning it can't be the device won't be able to detect the vibrations. Also, the freshness and authenticity of the messages are ensured by the use of nonces and timestamps. And NDNViber also provides the advantage of being able to rebootstrap devices. And being a dynamic technique itself, it uses new sets of messages, thus eliminating some of the common attacks, including man in the middle attack and replay attacks. The outcomes of our experiment shows that the time taken to transfer a byte using the discussed encoding scheme varies between 260 milliseconds to 380 milliseconds, based on the use of an appropriate idle period, which was 20 milliseconds in our case. The error rate is also seen to be of the order of 10 power minus 9, and the round of operation is effective in eliminating errors due to noise. Finally, on a commodity Android phone, it takes about 9 seconds for all the exchanges to complete and the IoT device to be successfully bootstrapped using NDNViber. In summary, we see that there are various out-of-band channels and auxiliary communication channels that can be used for bootstrapping, and we chose a vibration-based technique and named it NDNViber because of the advantages it provides for automated bootstrapping, for the option of being able to rebootstrap IoT devices, and also being able to bootstrap multiple devices at the same time. Finally, the security properties that NDNViber has is able to address most of the commonly seen security concerns that comes up when bootstrapping IoT devices. We are trying to benchmark the performance and optimize NDNViber design and provide a detailed security analysis, which is a part of our future work and ongoing work in this area. Uh, with this, I would like to thank you all for your attention and open the floor for discussion and questions. Thank you.